Now we would like to move into one of the topics for the aerospace world. It's the major one, rivets. Rivets are relatively low-cost, permanently installed fasteners that are lighter weight than bolts. They're interference fit, which makes them a lot different from bolts when you analyze them or put them in combination with other fasteners. And rivet installation is faster than bolt installation because it can be done in a lot of cases with automatic tools. Rivets work the best in thin sheet designs where shear is the dominant load, since a rivet really does not have very good tensile properties, tensile capacity. The rivets should also be designed to be critical in bearing, since you are normally considering them as a big pattern of fasteners holding a load, so since they have to work together, they need to be bearing critical so they can distribute the loads properly. The longer the grip length of a rivet, or that is the total thickness of sheets being joined, the more difficult it becomes to lock the rivet, because you're trying to compress all these sheets, and sometimes it's difficult to get them drawn up properly. Now, even though rivets are designed with an interference fit, they're not airtight or watertight. So if you want to seal a joint, you have to apply some type of sealant to the joint around the rivets. And here's another very important feature. Since rivets are permanently installed, they have to be removed by drilling or punching them out and replacing them with oversized rivets. And this is a real laborious task from the standpoint of both getting the old rivet out without screwing up the hole to where it's impossible to install another rivet in it without going to a much larger size, which might get you in trouble on edge distance and spacing and that type of thing. Rivet materials are made of various carbon steels, corrosion-resistant steel, brass, aluminum, Monel, titanium, and they have to be ductile enough that you can form a head on them without cracking. So you need a high strength, so it is a kind of a balancing act to try to get one that's ductile enough to form, but on the other hand, will have a high enough strength to give you the load carrying capacity that you want. Now, in Table 13, of course, is a list of some of the aerospace materials. And some of these rivets contain more than one material. They can actually come up with a hybrid rivet and use a softer material for the shop head so that you can buck the thing in place and still have a stronger shank. Here is a list of the common ones. Of course, the aircraft industry uses a lot of the ADs and DDs, which are the MS 20426 and 20470. The ADs are used normally up to a 5/32 diameter, and they can be readily formed at room temperature. The DDs, if they're made out of 2024, they have to be kept in an ice box until you're ready to install them, because you can only cold work them when they're down around 0 degrees without cracking them. 1100 aluminum, that's usually non-structural. A 5056 is a special one in this respect. They're still used. Some people are not aware, I don't think, that they are stress corrosion sensitive, and they really should not be used in anything other than a magnesium joint, where magnesium is more stress corrosion sensitive than the 5056, so therefore the 5056 will work out better. We had a case on the Atlas vehicle with 5056 rivets in which the heads were popping off with the thing sitting on the pad from stress corrosion, so they should not be used in most applications. Monel, which is a 67% nickel and 30% copper material is used a lot for rivets because it is ductile and yet it is higher strength than aluminum, and it's used for joining stainless steels, titanium, and Inconels. Copper is usually used for non-structural applications. The 7050 T73, that's the one that is not sensitive to stress corrosion, is used. It can be installed at room temperature, and it's used as an alternate to the 2024 icebox rivet. It has almost as good a strength as the 2024, and yet you don't have to worry about carrying them around in an icebox. Yes? Oh, it wasn't, is it picking me up?
Yeah, it's picking me up, and it's picking your tie up too.
Oh, it's picking the tie up too? Okay, well then we'll have to, okay, sorry about that. You want me to go ahead? All right. We move on then. Now that we got the microphone hooked up properly, we will move on to the head types of rivets. Now here are some of the common head types that are used. This is not to say that somebody else can have one of their own, because one of the things that you find is different manufacturers have their own ideas on how to manufacture fasteners, and so it is hard to get total standardization. Here is the common ones, of course, are the countersunk or flush head, and here is the flat that is used a lot. Now, of course, if on the planes that the jet planes normally have to have the flush rivets. Some of the older ones, I know we have an old Twin Otter here, I believe, that has the button head or flathead rivets on it because it doesn't fly fast enough for the drag to be that much of a problem with the protruding rivets. Moving on to the solid rivets, which are the ones usually used on skin construction on airplanes. They're a little bit different from some of the others, so we'll cover them separately. Here are the ones for construction, and that is almost a thing of the past, using construction rivets, because welding has pretty much replaced riveting in the construction industry. But anyway, for the construction type rivets, they're usually larger diameters, 5/16 through 2 inches, and are made of steel, and they can't be installed cold, so they have to be preheated to about 1800 degrees. Now, in the past, all the bridges that you saw had riveted lattice bars on them. In the old days, you used 4 angles and lattice bars to make your main truss members for a through truss type bridge. And the portal bracing on across the top, that's the part that holds the two trusses together as a unit, was also riveted. But on the newer designs, they use welded girders for that, so riveting is pretty much gone out with the times because of the labor costs. Now, if you're interested in construction rivets, there's still an ASTM spec, ASTM A502, covers construction rivets. Now, for aerospace usage, of course, you're talking about small diameters here, like an 1/8 through 1/4 of an inch. And if you remember on the drawings where you have the AD, like an AD5 or something like that, called out with the little X, it has the AD on the left-hand corner and a 5 on the right-hand corner. That is a 5/32 rivet. And so a big rivet in the aerospace industry is 3/16 or 1/4. You just use millions of them. So, and of course I had mentioned previously the 2024 T4 icebox rivet. And so since you have to have both sides of a rivet accessible, sometimes you run into problems trying to use solid rivets because you have to have a bucking bar on the manufactured head of the rivet, and a pneumatic hammer on the other end in order to form a head. So that brings up the subject of blind rivets. Blind rivets get their name from the fact that they can be installed from one side. And in a lot of cases, that's the only thing you can install. So they have the following advantages over solid rivets. There's only one operator required. The installation tool is portable. It's comparable to an electric drill in size. And you only need one side available for the workpiece. And you can use a variable grip length with a lot of them. Whereas with the solid rivets, the grip length is very critical on them. In order to head them, you can't go too long or too short. That's the part, the grip length is the part between sheets. So with the blind rivet, they're more adaptable. The amount of pull that you put on them, you can have some variation in the length of the shank itself. The installation time is a lot faster than for solid rivets. The clamping force is more uniform because you're pulling it with a machine rather than two people looking at it and saying, okay, this is enough. And you need less operator training. OSHA likes them better because they don't make as much noise. Now getting into specific blind rivets, here is one called, it's a pull mandrel type operation. And you just simply shove it in the hole from the one side. You have a serrated stem that you clamp onto with one part of the gun, and the head of it pushes against here to hold it in place, and then you just simply pull the stem through. When the proper load is reached, the stem is notched so that it breaks off, leaving you a fairly flush head. Now on a threaded stem rivet, you have pretty much the same thing except that your stem is threaded and you thread it through, and we have one of those or a couple of them in figure 48. Here are two different types that you're actually threading it through, and you see the goal on this is to pull it up tight and form a shop head on this side by expanding the tubular type body of the rivet. In this case, you are pulling the thing up by compressing here, by pulling through by threading, and you're holding the hex there. Here is a drive pin rivet. These are not used in the aerospace world or in the industrial world. They're simple to install, but you're not sure just how they're turning out, because all you do is get them and stick them in a hole and take a hammer and pound that in, and it expands it out on this side to form a head. And if you're wanting to hold a couple pieces of sheet metal together in your shop, that's fine, but you don't trust them that far with the airplane installations. Here's another type of industrial rivet, a full tubular rivet, in which you're actually, this has a hole in it. You poke it through and pound it and flare this end out and form a head on that side. It's a weaker rivet than some of the others because you see the wall thickness right in there is not that much. The semi-tubular rivet is pretty much the same thing, except the hole is not drilled in as far, so you get more solid shank in the hole, which makes it a little bit better. Now, with all of these, one of the things you have to keep in mind is they have to be ductile. So ductility goes up, strength goes down. So this rivet is not a very strong rivet, because if you made it very strong, then it would crack when you formed a head on it. The metal piercing rivet is, you actually drive it into the second sheet, and so that one flares out and creates a head like this on it when you drive it through the sheet. And this one is okay for sheet metal installations, that type of thing, but it is not considered a structural type rivet either. And here's one that goes back a ways. These have been around a long time. The old farmers used these to repair harness and things of this nature. This is the split copper rivet. And although I couldn't find a picture of the holder, there's a little wire holder that you put these in so that you don't pound your hands with them. And all you do is lay the two pieces of leather down, and these things are fairly sharp on the points, and take a hammer and pound the thing through the leather. And once you get it through, then you get it spread here and go ahead and pound a little more, and you clinch it. And it holds quite well on harness, straps, things of that nature. Now here's everybody's favorite for home use, the pop rivet. And just to satisfy the people from Black & Decker who wrote a nasty letter about the fact that I hadn't changed their name over to the association with this, because it used to be United Shoe that owned the company. Pop rivets are blind rivets used for home repairs. And we mentioned earlier about repairing fenders of cars with duct tape, that was a non-structural type repair. Pop rivets work better because they have a nail type stem, which is gripped by a handheld gun, and you drill a hole, stick the thing in, pull it through with the stem, then the stem breaks off. Sometimes it falls out altogether. And then you put Bondo over these to keep them from rusting, and sand them down, and you got a good repair job. But they're not a structural type that you would use on an airplane. Here's an example of the installation of a pop rivet, where you start out by poking the thing through, and this is bulbed back here, and so you pull it through and expand it back here, and you have yourself a decent rivet to hold a couple pieces of sheet metal together. One of the things with these that you got to watch about, though, if you are repairing aluminum gutters or something of that nature, make sure that you use the aluminum rivets rather than the steel, because then you get into the galvanic corrosion problem that I mentioned earlier. If you use steel rivets, they'll rust up like crazy in the aluminum because of the galvanic corrosion. So, and they do make aluminum pop rivets that you can use on aluminum, and the others for steel. Now here's one that is used some in the, I believe in the aerospace world for secondary type structures. It's a riv nut made, as far as I know, it's still made by B.F. Goodrich. It's a tubular rivet with internal threads, and you deform it in place to kind of form a nut plate. And if you look at the next picture of one, I think it will show how you do it. See, it's actually a bolt, if you will, with a threaded piece here. You stick the thing through a hole, then you hold it up here while you twist the threaded part of it and actually pull this up and deform it to where you get a installed nut plate, which then you can use to install fasteners in. And those have been around for several years, and we haven't used them around here, but they are used some by people in the industrial and I believe on secondary aerospace structures. Okay, for the now for the AD and DD rivets, we mentioned those earlier, the fact that those are the most common ones, the most preferred ones. And one of the things that I wanted to point out on this that was called to my attention by one of the guys from Lockheed Martin is that they had had some problems on using rivets that were not exactly the same material as the skin. Because when you think of it, at 45,000 feet, you have about minus 65 temperature. And on the runway out in Phoenix, you have about 140 degrees on the skin. So you need to have rivets and skin that are very close metallurgically in order to prevent differential thermal loads. And they had had some trouble and had to change to fasteners that were exactly the same material as the skin in order to get away from that. And the icebox rivets I mentioned earlier are have to be installed at 0 degrees, which makes them not very popular. The other thing, too, you run into a problem with them. If you don't use a batch of them, you have to take them back. If they've been exposed to room temperature for very long, you have to take them back and reheat treat them before, and then cool them down again before you can use them. So sometimes they've had trouble with people shortcutting things, saying, oh, well, they weren't out that long, so therefore we'll just go ahead and reuse them, and then they get rivet cracking. So they're very hard to control to make sure that you get a good heading operation on them. The 5056 I mentioned is stress corrosion sensitive in all materials except magnesium. And now here's one of the things, too, that is very important. Solid rivets are expanded to an interference fit. So they should not be used in composite materials because the hoop tension in the hole in a composite material can cause delamination of the material surfaces. So you should use a tight fit but non-expanding type rivet in composite materials. I had mentioned Monel rivets earlier. Monel, of course, is 67% nickel and 30% copper. It is stronger. It has a shear ultimate of 49 KSI and more heat resistant than aluminum, and yet it's ductile enough to cold form without cracking. And they're used for joining stainless steel, titanium, and Inconels, but it shouldn't be used for joining aluminum because it is way down in the galvanic series compared to aluminum, and it also, of course, would have different thermal expansion properties. The titanium columbium rivets, this is a hybrid one that is, well, they actually have two types. There's one that they actually join two pieces together, I guess, and this one is just the one that is part columbium. And they have a shear strength of 50 KSI, but they can be formed at room temperature. And they're used for joining titanium and aluminum because they have enough columbium in them to make them compatible with aluminum. And they generally don't need to have the corrosion protection on them except for sealing in the hole when you install the rivet. Now here is the table we showed earlier on this, so I won't go through it again, but just to let you know that these two are the ones you concentrate the most on in the aircraft world. Now here's the cherry buck rivet. That's the one I was thinking of. It actually has a friction welded piece of soft titanium on it, so that when you form it, most of the harder stuff is in the hole, so you only have a little bit of the softer material in the hole, so you get a higher overall strength, because this one has a shear strength up to almost 95 KSI, which is excellent. And they can be used up to 600 degrees, and they're available in both flush and protruding heads. Now, cherry rivets are a very popular one. In fact, they're almost generic, although Allfast and some of the others would not want me to say that about it since they make competing rivets. But a cherry rivet is a blind rivet with a locking collar, and you have a pull stem on it. but it is a better structural rivet because they have better materials in it than say a pop rivet would have. They're also available in oversized diameters, where if you have to replace a rivet, of course, when you drill the old rivet out, then you have to ream the hole to get it prepared better, and that takes enough material off of it that you can't get an interference fit, so you have to use an oversized rivet. So they make specific oversized rivets in given sizes. I forget now how many thousands they are oversized, but they will fit a reworked hole. They have shear strengths comparable to the AD solid aluminum rivets, and they're used a lot on secondary structures, but they're not used on primary structure. You normally use the solid rivets on primary structure in an airplane. Now, note that all of these blind rivets, along with Huck and Allfast, is restricted by the guidelines. Here's an MS spec that tells you how you should use them. And there's the statement also about the secondary structures versus primary. Here is the part of a installation in which you have the gun here that holds the head in place. Then you start the process of pulling the stem through to expand it. If you go on to the next figure, you have the completed installation. There's a little locking collar. This is the part that's shown in black here, that comes in and is pushed in around the shank after you have broken it off, which gives you a good seal on it to make sure that the stem stays in place on it. Now here is a table of cherry rivet materials, and notice that the stem and the sleeve are different materials, because the stem has to be strong to pull through and deform the sleeve. The sleeve has to be ductile enough to form without cracking. So you have, so the strength of the rivet is a combination of those two materials. So like here, if you have the 5055 aluminum with alloy steel, Manel with stainless steel, and here's an Inconel 600 with an Inconel X750 pull stem on it. And look at you can kick the temperature way up by going to the temperature resistant nickel stainlesses. Now Huck is also one of the big suppliers of rivets. Theirs are similar to cherry. In fact, if you look in Mill Handbook 5 for rivet allowables, there are a lot of them in there, and I know in our Fastener task group, one of the things that we have argued and fought over there is trying to come up with allowables that will include all of these manufacturers under one heading, so that we won't have problem with somebody saying, and you're favoring our company versus company X and so on. So you have to come up with a generic table to give allowables for this type of rivet, so that it'll cover Huck and cherry and Allfast. Now, move on to the next figure, and we'll look at a standard Huck rivet. See, this is pretty much similar to the other one, except in this case, you're compressing the sleeve a little bit this way, but the principle is still the same. You have a locking collar, you have a serrated pin that you pull through, and then after you pulled it through, it's notched here so that it breaks off, and you have the completed rivet installation. Now, here is a Huck clinch rivet, which is a little bit different. It has a separate sleeve here that compresses inside when you pull the thing through and kind of gives you a seal on it. That one, I'm not sure how widely used it is by the aerospace companies. I did not get a benchmark on it from any of the companies prior to this course. Now, Allfast makes several types, both solid and blind. And their wire draw rivet has a tapered stem bulb, and so that it expands the tubular body, which is a little bit different than the regular cherry and huck. So you see this one, I guess it shows up better over here. This is actually tapered so that it pulls through and keeps expanding as it pulls through, whereas the other one was a solid type. But the final installation there is the same, because you wind up with the thing pulled through to expand it, and then you have the locking collar around the stem at just inboard of where it broke. Now, high shear makes other types of rivets, and one of the ones that they make is a high-strength stem with a swaged collar that you put on it, and and this one, the collar is sized such that you can look at it from the outside and inspect it to tell whether it was installed properly. So if you turn to figure 61, this is a high shear installation. This is usually a 2024 T4 collar, and you just pull the thing through, swage it on here, and the way that it swages on, you can look around the top of it here and see whether it was formed properly so that it can be inspected from that side. Now, this is not an expanding rivet. That's the difference. This one, these are used a lot for installing brackets that are structural type things to heavy frames and so on in planes, where you want a real good fastener, but you'd rather not use bolts and nuts, because you can get these would be installed in a drilled and reamed hole, so it would give you a tighter tolerance on it. Now, lock bolts are also commonly used, and they are a non-expanding high-strength fastener that has either a swaged collar or a threaded collar to lock them in place. It's a variation of the high shear that I just showed you there, except that in this case you normally have a stem that you compress the collar on. A lock bolt is similar to a rivet in one respect. It's hard to remove once you install it. And it's not very strong in tension, because once again it's a metallurgical balancing act. You want the collar to form, but on the other hand it can't crack, so it can't be nearly as strong as the shank. So what you have is a fastener which is very strong in shear but is weak in tension, so normally you try to design them such that they're not in tension. Now, they're difficult to inspect, so if it's something that you need to have a more positive lock on, you should look for a bolt and nut assembly. But they're fast to install. And on the next page is one type of lock bolt. This is a Joe bolt. And what you have here, the locking sleeve or collar is expanded to form a shop head, because you're rotating the stem in a gun and holding the hex head in place. So you're running this through as threaded here to expand the sleeve to form a head. Then the stem is notched so that when you reach the proper torque, it breaks off. Now the huck bolt is a one with serrations on the shank rather than threads, and it's swaged in place. And the one thing about them, since you don't have threads, they can't back off because you just have straight serrations. So they're used a lot in the trucking industry for putting truck bodies together, because they're available in fairly large diameters. You can get up to about 1/2 inch diameter on them. And of course, they're very good in fatigue because once you put them together and clamp that collar on, they can't come loose very well unless the collar would actually break. And they're available in carbon steel, stainless steel, and aluminum. And on the next page is Huck bolt installed. And you see what they have is a notched stem. You pull the thing in place. There's your unserrated shank that you put in the joint, and then it breaks off once the thing is the collar is swaged in place. Now, High Shear makes a high lock, which is a similar one, and it has to be fed through a hole from the far side and held with a key to prevent rotation while the nut is being torqued with a tool. Then the outer portion of the nut breaks off on this one. Now, the high locks are available in super high strength materials, the alloy steel, H11 tool steel, stainless steel, and titanium. Now, one of the things I wanted to call your attention here, though, the H11 tool steel, which has been used in the past by SPS for a lot of their super high strength bolts, is stress corrosion sensitive, and some of the companies have kind of backed off on using it or using it in the real high strength. See this 156 KSI shear, that is, that's about a 260 heat treat bolt, so the elongation gets pretty low on it. And if it's stress corrosion sensitive, then you have to really do a good job of protecting it in order to assure yourself that you're not going to have some problems. Now here is a high lock, the installation. Now this is threaded on. So the threaded diameter is a little bit smaller here so that you can slide it through from the back side without screwing up the threads. Then you hold it. It has a internal hex in it, so you put a key in it with the gun to hold it in place, then tighten it down. The outer part of the nut that you're torquing with breaks off when you reach the proper torque. Now here is an unusual one. The high TIG is a high lock which is actually driven into an interference fit hole before the collar is installed. And of course, because you have the threads are slightly smaller, you can do this. Then, of course, the interference fit increases the fatigue resistance, and it actually will hold it in place while you are tightening it down. And I don't have a picture of one of them with this. The taper lock is made by SPS, and it has a threaded stem, tapered shank, and it's installed with an interference fit in a drilled and reamed hole. Now, the tapered shank that's only a 1, and don't ask me how this becomes a critical thing. It's a 1.19 degree taper that it has on the sides. And you lubricate the shank so you don't have to do anything to the hole, you just drive the thing in. But this interference fit keeps it from rotating while the lock nut with a captive washer attached to it is installed, and there is a picture of one of them in the next figure. So you have, this is kind of showing this way, although in reality it isn't in steps that much. You would not be able to see the steps on it due to that slight angle. But then you install it with this nut on it, and you can, since it's driven in place, the friction will hold it while you're installing the nut. Now next here is an eddy bolt, and they're used a lot by Boeing in the airplane business. I understand they use millions of them on the 777s, the 747s, and so on. And it's kind of an oddball, in my opinion. It has a deformed threads such that you use a kind of a socket type head that deforms to the point that it starts slipping, and then you know that it is installed properly. So be easier just to go with the picture on the next page. Maybe, I guess I better work with this one. This one has a fluted threads on the stem. Here you can see it. And so you start out, you have a nut that has these protrusions on it, and you have a special wrench to fit on that. So you tighten the doggone thing until the nut deforms to where these protrusions push it in, and it pushes in and locks on these flutes here. And then when you start spinning, you know you have the proper installation, which is kind of strange, but they work. Then they have another type that has a swage collar, like the ones the lock bolts that I've been showing you. And on that one, of course, you need a bucking bar on the back of it to hold it in place, because you're actually pushing down here and deforming the collar around it. But the locking is the same. It still has this type of shank on it. This shank is the same as this one. And those are used extensively, and they're fairly new. They've only been around for a few years. Now here's, remember earlier I mentioned that you don't want to use solid rivets in the composite materials, fiberglass, reinforced plastics, this type of thing, and all because it will start unraveling at the surfaces. Well, here is one made specifically for composite materials. It is a titanium lock bolt, and instead of, it has a 130-degree head on it, because you don't want the countersink very much on them, because you want to avoid the grinding on the surfaces as much as possible because of the reinforcing fibers. So this is a very flat, big head that they have on them, and that gives smaller contact stresses on the composite surfaces. It's a tight fit, but not an interference fit. Then they have a different type of serration on them, that they have a 20-degree angle here instead at 20 and 40, rather than the 30-30 that you would normally have on a notch on the serrations, to give you better holding power, because now with this flatter angle here, you can, when you put the collar in place, it's harder to pull it off, because you're trying to pull against that angle when you install the thing. And here is one of them installed, and now see notice that how odd this head looks, because it's 130 degrees instead of 82 or 100. Most of the aerospace stuff is 100-degree countersunk head. And then see it's installed very similar to the rest of the lock bolts and stuff like that. It's a collar that is pushed in here. You have a pull stem that breaks off when you've reached the proper load on them. I believe Monogram Fasteners is the outfit that makes that one out of, well, they're one of the companies out of California. So, general guidelines for selecting rivets and lock bolts. Don't use expanding rivets and composites, as we've talked about here. Don't use 50-56 aluminum rivets and anything other than magnesium, since the 50-56 is stress corrosion sensitive. A threaded lock bolt, that's one of the ones that has the nut on it that actually threads on and then breaks off the outer portion of it, can carry up to the tensile allowable of the shank, but each design should be checked individually. And since drilled fastener holes are not plated or coated, it's necessary to use some type of sealant over the raw material surfaces to retired to prevent galvanic corrosion between the fastener and the joint material. And of course, you can find lots of information on joints and rivet allowables, which were determined by tests in Mill Handbook 5. I think it's Chapter 9 of Mill Handbook 5 has all these joint allowables, rivets. They cover, they give you a table of rivet in a given thickness of material, how much it'll carry in shear. They even show the knife edge cutoffs. Remember I talked about the knife edges yesterday to avoid. They show where you cut it off to make sure you don't get knife edges and all that type of thing. Rivet installations are covered by Mill Standard 403. Some corrosion prevention methods are covered by these two mill specs. Design and selection requirements for blind structural rivets are given the MS 33522. And testing of fasteners is covered in Mill Standard 1312. That is a huge document, which I will, at the end, somewhere along the line, I have a listing of all the different tests that are covered in that document. It's a whole 3-ring notebook of standards for the different testings, I think 30-some sections or something like that. Then this NAS 523 gives rivet codes and callouts. That's the one that covers, I believe, the little X with the different designations on it for how to call out a specific rivet on a drawing, whether it's counter something near side, far side, and all that business. And then one of the other important things, review the fastener manufacturer's design criteria before incorporating his fasteners into your design. And that's one of the things that Dave Petrarca found out. Call the manufacturer and find out what his fasteners sell for before you decide that you're going to use a few hundred of them on your design, because they can get expensive, particularly in small quantities. Now, moving on to inspection and acceptance of fasteners. This is one of the things that is not covered very well by most people, because we can specify all the things that we want in fasteners, and but when we get them, we don't necessarily get what we ordered. And the criticality of the fastener design should determine how much inspection we have on it. So we'll cover some of the inspection methods that are used. Now, on ordinary fasteners, bolts, nuts, and stuff like that, we can use hardness testing. That's a simple one. You use Brunel test for aluminum, usually, and Rockwell for steel. And what these in general do, you have a little ball that gives you an indentation, and the amount of indentation that you get is correlated to the hardness of the material, and that in turn to the strength of the material. So, for example, if you go to a table, let's see, a grade 8 fastener is about a Rockwell C33, I believe. And at least it gives you some indications. And that's an easy test to run, because you have a little machine. You just slap the thing in there and run the test, or at least a beginning test on it. The Brunel is used for testing your aluminum stuff, usually, although Brunel and Rockwell can be correlated, because Wilson Company makes all this equipment, and they put out tables that give you the correlation between them. You also have a Rockwell B scale for medium hardness materials. Usually your carbon steels are rated on the B scale, and then when you get up, I think a B100 is equivalent to around a C 18 or 20 or something like that for the harder materials. So if we go to the next figure, here's a Brunel hardness tester, And what you have is a little table that you put your sample on. The ball is in the head here, and you actuate the thing. This is an older one, I think, when you just used a handle to actuate it. Nowadays, they probably, on these, they probably make them that they are electronically actuated. That one is for the aluminum. And then here is the Rockwell. This is one of the newer Rockwell models that I got out of one of their catalogs, or Wilson catalog. Same thing, you have a head here to put your sample on, or platform, and then you have the ball is in this part of it. You program the thing to give you a given amount of load, and it measures the indentation and gives you a reading, which you can use with the table to check it out. This mill standard 1312-6 gives a standard test method and specifies the apparatus to be used for hardness testing in all types of structural fasteners. Now, the B scale, this is the size diameter ball and the load that you use with it, and then the C has its own diameter and the load. And here's another one, a Rockwell superficial hardness tester, except the indentation is smaller. And then Knoop and Vickers micro hardness testers. Some of these, they have them small enough that you can actually take them out on the job and test your parts without having to pull them out and take them into the shop, the metallurgical lab, to get them checked. Now, for fastener hardness testing, one of the problems you run into, of course, is how do you get an accurate reading? And if you have cold worked the fastener in forming it, if you take a reading on the outside someplace, it may not necessarily be the proper strength. So to get accurate readings, you need to get core hardness. So you can take machine it down and get two flat parallel surfaces and use one of them for hardness testing. And the other thing you can do, if you have small fasteners that you can't do that with, then you can mount them, and these metallurgical people can put them in a nice little thermoplastic type setting that you can then put it on the platform and get hardness testing. And the beauty of that is, since you can't get through hardening in a fastener in a lot of materials above about 3/4 inch diameter, so you need to take both hardness readings close to the threads and at the core to see whether you're getting the true strength indication for the fastener. So on the little ones, this is a 0 to number 5, so that's 60 thousandths to an 1/8 diameter. And same thing for rivets, you can set those. And then on larger ones, you can there is a way of measuring the shank, if it's not co-worked too much, that you can get a ballpark type reading if the thing is big enough. But this is not a very accurate reading. It's only if you're wanting something, just a general type reading. Now, tensile testing. This is something, of course, you can do, and they do a little bit of that around here. Carl Bergquist is the guy that does it, on taking a few samples out of the grade 8s and socket head cap screws and pulling them just to see what they are good for. So in general, you take a few out, run them. If any of them fails, you reject the lot. And what you do is you use a regular tensile testing machine that has large enough fixtures that you get essentially no deformation from the fixtures themselves, because you want all the deformation to be in the fastener. That way you can even measure the yield, ultimate strength, and elongation. Here's another test that can be used, and of course counterfeit fasteners most of the time are made by cheating on the carbon content. In order to heat treat a fastener, and we have in the specifications for a alloy steel fastener, it has to be a minimum of 28 points of carbon in order to get heat treating, and usually you use them up around 40. So the counterfeiters can add boron, increases the hardenability of steel, and boron is cheap and you don't need very much of it to add. So you can take 1020 steel and add a little boron to it and heat treat it. So one of the tests that is used on acceptance of alloy steel fasteners is a carbon content test. And there's different ways of doing it. One of the company that I believe makes the equipment that we have around here is called LECO. And what you have is some type of a furnace in which it's either an induction or high frequency type or resistance type furnaces, and you take a little chunk of this stuff and put enough oxygen in with it that you can burn it. And then you have different ways of measuring by getting the carbon dioxide from the combustion. You can measure it and get the carbon content out of your sample. So I'll kind of go into this in a little bit more detail here for a couple minutes yet. It's high temperature combustion, and you have two types of furnaces, the high frequency and resistance high temperature. And you use two different methods of carbon sulfur detection. Infrared absorption and thermal conductivity are the two different methods that are used for it. The test theory, of course, is to determine the content of carbon and sulfur, and you can separate them out and find out which is which. And you get carbon dioxide and sulfur dioxide. And so with this furnace, you have to take it up to a pretty high temperature, even with the oxygen, to burn the carbon off of the steel, because steel doesn't burn very well. The other oxide compounds that you get during this combustion, you can siphon them off and get them out. And you also remove the moisture with some sort of a dissicant, such as Harold even put in there what they use, magnesium perchlorate. Harold Casper helped me on coming up with all of this stuff. The samples, here's one of the important things. You have to make sure that you know exactly how much weight you have in your sample in order to do the testing, because what you're looking at is the carbon per weight in it. And since it's such a small amount, the weight of the sample has to be accurate. The limitations on it also, the specimen must be homogeneous. In other words, I spoke of the decarburization. If you had, say, heavy content of carbon in the surface of the thing, due to the way it was heat treated, then you would get an erroneous reading. It would show that it had a higher carbon content than it really had throughout. Graphite bearing specimens you have trouble with. In other words, you can't have graphite on the outside for a lubricant. And of course, the method is destructive. So getting a sample and weighing it is a fairly short thing. And then the high frequency furnace that they use it actually has a coil, a heating coil on it, and you have a ceramic crucible that holds the sample, and you heat it up and cook it out. And here's one of them on the next page. Then we will take a break, and we'll look at it when we come back.